Well, with functions handled, let's move on to arithmetic. Arithmetic operations, plus, minus, times, divided by, are just like functions, but they take two arguments. So the way we deal with them is necessarily a bit more complicated because there's two arguments instead of one. But the basic idea is the same. Let me do a quick example. 1 plus plus 2 plus, just to do a very, very easy one to start, to see how you're supposed to deal with these mathematically. For a function, the way a function operated on these objects was apply that function to every single number in that interval. For an arithmetic operation, what we do is apply that operation to every pair of numbers, one from the first and one from the second. So for instance, what sorts of numbers are in 1 plus plus 2 plus? Well, there's numbers a little bit bigger than 1, varying distances away, and numbers a little bit bigger than 2, varying distances away. The results are a little bit bigger than 3 and varying distances away. If we view it, it looks like that. It's twice as big as our standard 3 plus, but who cares? As you squeeze the inputs, what happens to the results? Just like with the function case, there's just not a graph here because there's too much information to graph. Just think about the numbers. I think it's pretty clear that what we're seeing, if you just look at the results, is 3 plus. So 1 plus plus 2 plus is 3 plus. Great. What about 1 plus plus 2 minus? Well, there's something to think about here. What results do you get? Well, the first thing is obvious. Numbers close to 1 and numbers close to 2 are going to add up to numbers close to 3, but which side do they live on? Well, you could have a number a little bit bigger than 1 added to a number a bit further away from 2, which would net effect a little bit bigger than 1, a lot smaller than 2, would leave you to the left of 3. You could have numbers equidistant, some distance away from 1 and some distance away from 2. If you add them, you'll get exactly 3. Or the plus part could win. Something a lot bigger than 1 plus something a little bit closer to 2 would give something bigger than 3. The results are here. You get numbers bigger, smaller, or equal to 3, but close to 3. And the closer the 1 plus and the 2 minus squeeze to their locations, the closer your results squeeze. And again, if you just look at it, it takes a bit more thought to think through the arithmetic, because these are where the complicated cases happen. But it can be done. The result is 3 plus minus dot. And you can see it. A student can just pause and think about this for as long as they like and make sure it makes sense. You can put in any operation, any objects you like, and you can see what comes out. To speed this up, let's just take a slightly more interesting case, 0 times infinity. This is something that I used to see a lot with calc students. 0 times infinity. You tell them it's indeterminate, but they learned a long time ago that 0 times anything is 0. So what's up? Well, I mean, the fact is 0 times infinity, 0 is indeterminate. The answer is, do the math. The number 0 times every single number in the plus infinity slice ends up as 0. In fact, 0 times infinity is 0, because 0 times anything is 0. That's not untrue. We don't have to go back on our promises to students on what's absolutely true in mathematics. You can guess where I'm going. On the other hand, 0 plus times positive infinity is an entirely different beast. It's not 0 times infinity anymore. It's not 0. The rules for 0 don't apply. So do the arithmetic. It's a more complicated case what we saw with 1 plus and 2 minus. Multiply all of these numbers by all of these numbers and see what comes out. Well, let's do a few. Always good to look at the extreme cases. Take, say, a quarter, looks like it's in this set, and multiply it by bigger and bigger and bigger positive numbers. You get huge positive numbers. On the flip side, take, say, 5, and multiply it by smaller and smaller and smaller positive numbers. We get tiny, tiny positive numbers. In fact, if you think about it, you can get any positive number as a product of one of these guys and one of these guys. So what we see is that old-fashioned interval 0 infinity, all the positive numbers. All right? What happens when these guys squeeze? Well, the 0 plus isn't what I've drawn for you. It squeezes, and so is the infinity. But as they squeeze, what happens to the result? Zoom in a bit as we squeeze. Answer? Absolutely nothing, because no matter how far we squeeze, the same qualitative things happen, and you can see it. This is a classical case of indeterminacy. There's something to think about, but it's all in front of the students now. Why is, no matter how far these squeeze, will we get everything as a result, every positive real number? Well, no matter how far I squeeze, I've got, say, 1/100th times huge positive numbers, huge positive numbers. I've got 100 times tiny positive numbers, tiny positive numbers. I've got 100 times 100th, which is 1. I've got every number in between. It doesn't matter how far they squeeze. Well, the computer is just going to say arrow star because it's not an infinity or a convergent guy. But this was the case we saw of indeterminacy. If you ever see a computation that comes down to 0 plus times positive infinity, that's an indeterminate form. That's the interval 0 infinity. Go back to indeterminacy. If your answer fit into the interval 0 infinity, what can you conclude about what you had? Well, lots of things hit this blue target. 0 plus hits it, 1 plus hits it, 1,000 plus hits it, infinity hits it. All sorts of things hit that target. If you're doing a computation and you end up with an arrow to this object, the answer is you can't determine anything from that information. Every indeterminate form, along with being memorized, can be fully sort of prodded at and poked until it makes sense. A quick remark about these indeterminate results, lest you think there's a problem here. You get indeterminacy with these objects just like you get indeterminacy when you do limits in the classical way, because all the definitions are the same, which we'll see later. The difference is you can see exactly why and how it's indeterminate now. What do you do if you get an indeterminate result now? The same thing you did before. If you push through a computation and it comes out to an indeterminate form, you go back before you tossed in these objects to the plain old x's and variables and numbers that you know so well from pre-calc and before, and you mess with the algebra. Now, a beautiful thing about these objects, which I haven't drawn up but you can think about it, is this. If you take two expressions that algebraically are equivalent and stick into them, say, replace all the x's with positive infinity, you can get two different results, but they'll be two compatible results. If I stick in plus infinity and get, say, an indeterminate result, I should be able to, if it's possible, rearrange my expression and plug in plus infinity again and get a result that works. The key selling point is here, whether it's an indeterminate result or a good answer, a student can show every step of their work along the way. I think sometimes with limits are numbers. Show your work. You can't show your work with limits and numbers because anytime an infinity occurs, you're not talking about limits anymore, and most of your limit laws aren't really in play anymore. We've got apples and apples here. The 0 plus, the infinity, the convergent, the divergent are all the same type of object. And if we can think them through, we can show our work, we can write our steps, we can check our work, and we can really get a better conceptual understanding of what we're doing, as well as a more accurate computational framework for working with these objects.